Hello friends, myself Rajib, a third year BTech Engineering Physics student at IIT Roorkee, and today we are going to understand and perform a very important experiment to study Hall effect. So the aim of our today's experiment is to study Hall effect and determine type of major charge carriers, along with charge carrier density and carrier mobility. So the apparatus we need for this experiment includes Hall probes, that is germanium crystal and indium arsenide crystal with spring type contacts and soldered contacts respectively. We need a digital Hall effect setup consist of an electronic digital voltmeter and a constant current power supply. We need three variants of electromagnets with maximum field intensity of 12.5, 7.5 and 5 kilogauss. We need a digital Gauss meter and a power supply of 220 volt of 50 Hz. So let me take you through the basic theoretical part. So when a static magnetic field is applied on a conductor perpendicular to the direction of the applied voltage, the charge carriers experience additional interaction force due to interaction with magnetic field. This results in separation of charges which generate electric potential across the conductors in the direction perpendicular to that of the field. So as you can see in the diagram, so this is the direction of the current, and the magnetic field is applied perpendicular to the direction of the current, and we get a electric potential or electric field uh, in in the direction perpendicular to both current and the applied magnetic field. So the whole coefficient is given by the expression Uy by Jj into B. B is the magnetic field, Uy is the electric field, and J is the current density. And this can be reduced down to this expression. And the mobility is given by Hall coefficient into conductivity. So for the case of intrinsic semiconductors having two types of charge carriers, quantitative description of Hall effect is not that simple. And mobility of charge carriers also need to be considered. Hall coefficient in such a case is given by this expression. Here mu h and mu e are the mobility of the electron and holes respectively. Thus mobility mu h and mu e themselves vary with T and R, may become 0 or change sign. Hall coefficient inversion is a peculiar property of p-type semiconductors. Thus R in conjunction with resistivity measurement can provide information on carrier density, mobilities, impurity concentration and other values.
So, hello friends. Today we are going to perform the Hall effect experiment. So let me first describe the apparatus briefly. So as you can see in this apparatus, we have the digital Hall effect setup, in which there is a ammeter and there is a voltmeter. Through this ammeter, we measure the current that is passing through the semiconductor, and here we calculate the Hall voltage. And there is the digital Gauss meter. Here we measure the magnetic field, and this digital Gauss meter is connected to the Gauss probe, and it measures the magnetic field between the two electromagnets. Now let's come to the constant power supply. So as you can see, this constant power supply is used to pass current through the two electromagnets. Here one thing to note, that we are not that much interested in knowing what is the current passing through the electromagnet. We are rather interested in what is the magnetic field that is we are getting here. Okay. So now come to the first part of the experiment. So for the first part of the experiment, we will see a linear variation between the current passing through the electromagnet and the magnetic field produced here. So as you can see, there is some zero error, so we can zero adjust it. But if we increase the current passing through the electromagnet, like at 0.5, we are getting almost 547 Gauss. Now if we double it to almost 1, we are getting almost close to 930. So there is a linear variation between the current passing through the electromagnet and the magnetic field produced in the experiment. Now let's come to the second part of the experiment. So for the second part of the experiment, let me describe about the Hall probe. So for the Hall probe, as you can see, so there is the semiconductor and of length T and of thickness T and width B, and there are two types of connection. One is lengthwise connection and one is breadthwise connection. So for the breadthwise connection, as you can see, there are two red wires which are connected to the voltmeter of the digital Hall effect setup, And for the lengthwise connection, we have two green wires that is connected to the ammeter of the digital Hall effect setup. Now what we will do in this experiment is that we will make this Gauss meter to a constant value, so that we are applying a constant magnetic field. So we can do this by uh, keeping a constant current through the Gauss meter and for a particular value of the magnetic field. So now we will put this Hall probe here in a stable position. So now what is happening actually is that we are passing a current and there is a magnetic field perpendicular to the semiconductor or sample, and we on this digital Hall effect setup. Now we can vary the current passing through the sample, and we can measure the voltage, the Hall voltage. So as you can see, at almost 4.1 it is coming almost 3.6, and now we can change it to like 9 9, and we can see the Hall voltage is 7.5. So we can do this variation of the current and the Hall voltage. So in this way we can measure the relationship between the Hall voltage and the current passing through the semiconductor. So that was for all today. We will go to the observation table in the next slide.
So let's come to the observation table. So the first table is the Hall voltage versus magnetic field, and we have done this for sample 1, that is p-type germanium, and a constant current of 2.47 mA. So as we can see from the table in both forward and reverse, there is a linear variation between magnetic field and Hall voltage. And for the second part of the experiment, we have varied the applied current, and we can see that a variation of Hall voltage here. So we have done this for one sample, that is the p-type germanium. You can do the same thing exactly for the n-type also. And we have here kept a constant magnetic field of 185 Gauss. So now if we plot the applied current versus the Hall voltage, we can see a very good linear variation between these two. And from this curve, we can measure the slope of the VI curve, which will be required to calculate the Hall coefficient. So the slope of the v versus I curve is given by RH to B by Z. So you can get this expression from the theoretical part also that I have shown earlier. So if we put all the value, we get the Hall coefficient as 0.0039 m cube inverse, and the carrier density comes out to be 161.5 into 10 to the power 19 meter minus to the power minus 3, and the mobility is given by this expression, this value. So the result that we are getting from this experiment is that the RH is greater than 0. That implies that carrier charge is positive and due to holes for p-type. You can perform the same experiment exactly for the n-type also, and you will get that the RH is negative for that case. So the precautions that we can and we should take while performing these experiments includes: calibrate the probe such that in absence of magnetic field the Hall voltage is zero nearly. Align the Gauss meter and semiconductor sample probe in the middle of the conductor. So that was all for today. I hope you have really enjoyed this whole experiment. So thank you all. If you want to ask any questions, you can do so by typing your question in the comment section. I will be more than happy to answer that. So thank you all.